Welcome back to the fifth video of this crash course in quantum processing. The last time I talked about the density operator and density matrix for characterizing qubits for wave functions in terms of decoherence imperfections that are normally inaccessible to Schrödinger. Today is the motivation for what we call the spirit of quantum mechanics, so the entanglement. So entanglement feature is very well known to a lot of people, even if it's just a name, but entanglement plays an important role in characterizing any quantum system related to another system. So it can be considered to be the spirit of quantum protocols, yes, the motivation to build quantum network, quantum gates, security, cryptography, and all of these nice stuff. And believe me or not, entanglement is an essential part that has to be covered in any quantum mechanics course, even if just a flavor. Here's just a flavor, quick flavor, and let me retrieve back the EPR pair. I told you before that's what I call the entangled state. So it can be written, yes, we know, it's very familiar to us, and here also is another way to write it down. If you come to 2 pluses plus 2 minuses, you can find that, yes, they are equivalent to 2 zeros and 2 ones here as an EPR pair. Why it's an entangled state? Well, because it's what we call non-separable state. What is called by non-separable state? What's called by non-separable state? If you think for a moment, you see that they cannot be separated from each other. What does it mean? It means that this, if I take an example of this state, which is 1 over square root 2 phi, 1 0 and 1 1, you can find that you can separate one out of it. So I can separate one out, I can tensor product 1 with a state 0 plus 1. And this is very separable state, okay? But an entangled state cannot be a separable state. Here you can find that this phi is encodes some information that are non-separable, okay? They cannot tensor product can be tensor products away from each other. And by the way, EPR is one of the most entangled states of 2 qubits, okay? One of the most entangled states of 2 qubits. And you will discover EPR even in few minutes. Okay. Important features of an entangled state or entanglement in general is the so-called the maximally correlation. Maximally correlated state means that if I measure in the basis of A and B and measure them in the same basis, I can find that the outcomes are actually identical, okay? Identical outcomes. Maybe 50-50, for example, for 2 states A and B, or 2 systems A and B. The other feature here is the monogamy of the entanglement. It's a very well-known monogamous feature. Monogamous feature allows us to say that the system is very entangled, okay? Entangled with each other, but unentangled or non-entangled from the rest of the world. So the state can exist as a tensor product, this state with universe. So you can separate, they're very entangled with each other as systems. For 2 qubits, for example, are very entangled, but they are very non-entangled with the other states in the universe, and they can be separated by tensor product state as I did here in separable state. Those are very important features to know for entanglement. And let's take an example for entanglement in terms of density matrix. We have to motivate for density matrix. Density matrix is essential to write down here. For density matrix, if it's entangled, I cannot get A out of B by tensor product state for some eigenvalues, probabilities that have to be larger than or equal to 1. Sorry, less than or equal to 1 for probabilities. And for an example of this, let's take an example of a density matrix that looks like this. Think a moment for yourself and try to indicate whether it's an entangled state or not. If you get it right, so you'll see that both here are actually non-entangled state, can be separable state, because you can separate actually pluses or minuses part of, or zeros and ones are parts of pluses and minuses. you can separate them out by tensor product, and this is a separable state in terms of a density matrix in A and B. Okay. So let's try to take another look at an application of this density matrix in terms of the entangled pairs. Okay, so the application is what I call the super dense coding. It's very important, and you can hear it from one of the pioneering work of Charles Bennett, for example, who got the Dirac medal this year, and also it's invented by Stefan Wiesner, and Charles Bennett are the kind of people who pioneered this super dense coding. Super dense coding means that if I have two parties, and two parties have kinds of transmission they want to be correlated by transmitting information from one party to the other, and suppose that two parties are Alice and Bob. So you have to be familiar from now to Alice and Bob's, because they're very milestones, are very important milestones in cryptographic protocols that we will be establishing in any quantum cryptography course. You find that, for example, if Alice has some classical information, okay, some 2-bit classical information, 1-1 can be 0-0, 0-1, 1-0, and she wants to transmit those information to Bob to measure. So the application of super dense coding says that, okay, I have to share a qubit, and this qubit of this kind. So I share pairs of this qubit to Alice and Bob, okay? And if Alice wants to send some signals, some information to Bob, she will operate over these kind of operations that we learned in unitary operation class here. So if I take, if I would like to, for example, let's begin with 0-0. I would like to send 0-0 to Bob, or Alice wants to send 0-0 to Bob. So she will apply nothing to 0-0, okay? Nothing to 0-0, and it will be transmitted easily here. But what if she would like to send, let's begin with 1-0, okay? So you will apply the quantum knot gate. So x applied on a wave function of quantum knot here. You will find that it begins to flip this first, okay, and will flip also here second. This is number 1. What about if I would like to transmit 0-1, and I will apply the z over the wave function? It means that I just have a phase flip operation. Okay. Number 2. What about if I apply iy, which is nothing else than applying z, where xi will be here. It will be kind of inverse the sign with inverse the second one here. Okay. And this is the third. Actually, with the EPR, number 4, these are the so-called Bell bases or Bell states. So now we have fantastic recovery of the Bell states, and the most famous entangled states, or the entangled states that are of interest to all people in the field. So Bell states can be written like this. This is exactly what we got when we operated x, y, and z over the classical information or over the qubit to recover the classical information that Alice wants to send to Bob. So Bell states are also called the EPR pairs. Okay, so those Bell states are actually orthonormal basis characteristics. So normal basis, form orthonormal basis characteristic. And if you'd like to measure by doing some measurement in the Bell basis, actually Bob can recover what Alice sent to him. So this was just a flavor of the entanglement and the application of super dense coding. You will hear quite a lot about it, and The next videos will be responsible for delving into the information theory, the quantum information theory part, after some establishment of these basics that we did. Thanks a lot for watching, and see you in the next video.